So here we're at the Capsim TMK repository on GitHub, hosted on GitHub by Silicon DSP. And what I want to show is when you scroll down, there's this link to getting started for Capsim text mode kernel. Let's go ahead and click on that. And this is a very important link. So it shows all kinds of links and details, documentation, setup, instructions for building Capsim, which we're going to cover in this video. Now, a key point I want to point out is that over here, there's a link to basically setting up Capsim on Linux. So this is basically setting up C++ and C and certain libraries on Linux before you build Capsim on Linux. Okay, so let's go ahead and hit that link. So basically, it's about setting up a C++ development environment with libraries to build Capsim as shown here. So make sure you go ahead and install these tools. For example, we have tools for TIFF libraries for showing images and other tools, especially for Makefile and so forth, and C++ development, and also compression, etc. So just follow these instructions and you'll be ready, set, go. Plus, it's a great bunch of tools to have available when you're doing serious C++ development on Linux. Okay, so now we're in the Capsim repository on Silicon DSP on GitHub. And what we're going to do is show that how to download the repository as a zip file and then unzip it, define the path to Capsim, and then go create a working directory and build a Capsim executable so you can build block diagram simulation systems for DSP communication, other applications. Okay, so let's get started. So we're in the repository. We go to this code and just say download zip and say save. So this will normally on Linux, it'll save this in the download directory. Okay, so now let's go to the console, and what we're going to do is make a directory called Capsim. This is in the main path. We're going to change to the Capsim directory. And here we're going to copy the zip file from the download directory to this directory. So let's go ahead and do that. So we're going to copy from download to this directory. Okay. Now we're running Linux Mint, by the way. So Linux Mint based on Ubuntu. And we're doing an Intel architecture, 64-bit x86. Okay, so let's go ahead and do an ls. There it is. There's our zipped archive of the Capsim repository. So we'll say unzip, very simple, unzip Capsim. So that's all we do. Here we go. It's going to unzip it. And if I do an ls now, you'll see that we have the directory called Capsim TMK main here. And what we need to do is change to that directory. And the key thing we need to do is define a environmental variable called Capsim, all uppercase, that points to this directory. That's all we need to do. And then we'll create a work directory and then build an executable Capsim there and start running simulations, building systems and running simulations. So one of the things we can do is say pwd, and this will actually give us the path. I'm going to go ahead and copy that. Let's use this trick and say export Capsim equals this path. So Capsim has to point to where the Capsim TMK repository is. That's it. So now that we've done that, we're ready to start work. So let's go ahead and clear all this. And what we're going to do is go back to our home directory and make a directory called work. Okay, never create this Capsim executable in the Capsim main directory. Okay, the source code. So we just created our called work. Let's go ahead and cd into that. Right now it's empty. Now here's the key thing. To build Capsim, it's very simple. We're going to run a bash script, a shell script in the Capsim repository. So we say source. Now notice that since we've defined where Capsim is, we get access to all the things like tools. And the key shell script we're going to use is pre-Capsim. So this is the bash shell we're going to execute, and everything is automatic. A lot of things will happen. Let's go ahead and execute this. Okay. Now, a lot of things happen here, which we'll explain, but you'll always get this message that it cannot access Capsim. That's because it did create a make file. Let's go ahead and show that. There's a make file that was created, and in order to obviously create Capsim, we have to say make. That's it. Type make, and there we go. It built a Capsim executable. Let's go ahead and take a look at that. So let's do an ls. And here is the Capsim executable that it just got created. So we're ready to rock and roll. Now, these directory called blocks and subs. Blocks is where you put your own custom blocks that you build, you design and build, and we'll talk about that in later videos. And also subs, where you would put your own subroutines, in addition to the subroutines provided by Capsim. So right now, all we want to do is run Capsim. We've already created it. Let's go ahead and type Capsim, and this is all you need to do is say Capsim-B. Okay, and this is the text mode version of Capsim which just showed up. Here we go. Okay, so right now we're ready to start building some block diagram simulations. Okay, so first thing we're going to do is create this block called sine. And what this block does is it generates a cosine and a sine. And if only one connection is made, it'll generate the cosine. If two are made, it'll also generate a sine in quadrature. Okay, here's a good command, info. There you go. So it tells you everything about this block, the current block that's active right now. So here we go. It's called sine 0. It automatically put the 0 there to distinguish it from the library and all its parameters. Now, due to legacy from Berkeley, from Blossom, blocks are sometimes referred to as stars because in that time they basically called blocks stars, and then if you had a hierarchy of blocks containing many blocks, they called it a galaxy. And if you had the whole simulation was called a universe, but we don't use those terms. We basically call it topology, block, or hierarchical block. Okay, so now that we have the sign, let's go ahead and create a probe called, now here we go. It's very simple. Say block print file. So create a block from the block print file. Now, if I go info, now we have a block called print file. Now notice its parameters. It's going to output right now to the standard out, which is a terminal. This is an important parameter, which is output control. So since print file is a probe, sometimes you just want to turn it off, which we'll do. But for now, what we're going to do is connect the sign block to the print file block. So we say connect. Now remember, we've got to put the 0 there, and then buffer 0 to print file 0, and its buffer 0. Let's go ahead and connect those two. See, it's that simple. You connected two blocks. Nice. So let's go ahead and use this command, display all. Very, very nice command. And it'll show you that we have the sign block, the print file block, over here, the sign block print file, and we connected them. Buffer 0 to 0. Okay, let's go ahead and do a run. So now we can run a simulation. There you go. So we printed everything to the screen, and this is just a sine wave, 128 samples. Okay, that's simple. Now, one of the things we're going to do is add noise and then add a spectrum probe and plot the spectrum and time domain. Before we do that, we're going to go to the print file, okay, and change parameters. This is a very powerful command, CHP. And standard out is fine, but we're going to turn it off. So if we say 0 for the output control, we just turn that probe off. In fact, right now, if I say run, you don't get anything. So I turn that probe off. The thing we're going to do is we're going to create a block called add noise, and we're going to add noise to the cosine wave and then send it off to the spectrum plot to get a spectrum plot. So let's go ahead and start that. So we say block add noise. Now, when you create a block, it's a default block right now. It's a current block, so to speak. So all you need to do is say CHP. One of the things we're going to do is change the noise power to 0.1. Okay? That's it. Now that we have the noise block, we're adding noise. Let's go ahead and create the spectrum block. Now notice that the spectrum, we say spectrum TXT because we're in text mode. Okay? So that's the name of the probe for plotting this, calculating and plotting the spectrum, and also the time domain. So now we have our blocks. Now, if I go display all, you'll notice that they're not connected. The only connection we have is between the sign block and the print file block. So let's go ahead and connect everything up. So what we're going to say is connect print file to add, buffer 0, to add noise, buffer 0. So, okay, so by the way, I mistyped add noise. So let's go ahead and say connect. Again, print file. Don't forget the buffer to add noise. Remember the 0 and then 0 for the block. So, and to verify this, we'll do a display all. You can see now we have a connection between the sign, the print file probe, the print file volt to the add noise. Now notice print file is a probe, so it'll just pass its input samples to its output buffers straight through. Okay, next step, let's connect the spectrum to the add noise. So we say connect add noise to spectrum. Okay, let's just do a display all so you can see what happened. So we have all the connections. Sign to print file to add noise to spectrum. Okay. One thing we want to do is we need to change the number of samples. Before we only had 128. We need to change the number of samples that the sign block generates to 1024. So what we're going to do is go to sign, and it went to the sign star. So that's a quick way to do that. You would normally put the whole name with a 0, but it figured that out. And if I do info, you'll see that the current block right now is the sign block. Let's go ahead and say change parameter. And instead of 128, we're going to tell it to generate 1024 samples. And then hit return for the defaults. Notice sampling rate is 32,000. And the frequency is 1,000, which is 1 kilohertz. Okay. Now is a good time to store our topology into a file. So we'll store this into a file called sign test. Always a good idea to do that before you do a run. And once you do that, the next time all you need to do if you change anything is say store. So right now we're ready to run. Let's go ahead and run. And we get two files that are created by the spectrum probe. One is a time domain with .tim, and one is in the frequency domain .fre. So we're done, and let's go ahead and quit out of Capsim and do an ls, and you can see that these two files have been created. First thing I'm going to do is we have a great tool that's supplied with the Capsim repository called IIP plot. It's a Java program that is we can use to plot these results. So very powerful tool. Let's go ahead and get that running, and we'll plot the time domain first. So to do that, all you need to do is just say java-jar and point to the tool, which is in the Capsim repository, so you can see that the environment variable comes in. And it is called IIP plot.jar. So what do we want to plot? Spectrum.tim, the time domain of the signal. Okay, let's go ahead. There we go. We got the plot. So this is a very powerful tool because for one of the things you can do, is just increase the size like that, and we can see the sine wave with added noise. Okay, now remember this is a cosine, and then if you add another connection, it'll generate the sine. This is a very nice tool here, which is a theme tool, and we can change to this theme, which is nice, sort of a scope-like color scheme. Okay, so here we have the time domain. You can also do things like zoom in and zoom out. Lots of options. But for now, we're happy with this, but I want to show you another nice feature is that we can plot the frequency spectrum and do some interesting things with that. So here we have the spectrum. Let's go ahead and expand this out a little bit, center it. And you can see the nice peak at 1 kilohertz. By the way, we can change all these so that it displays everything in hertz. And so we have a nice peak here, and we have the noise. And let's go ahead and change the theme. There we go. Now we're going to do an interesting thing. With this tool here, we can modify the axis. And right now I'm going to say that we want the y-axis to be logarithmic. So I hit the fixed point logarithmic, say apply. There you go. So we have a logarithmic scale for the spectrum. Okay. So let's go ahead and show another feature. Let's go ahead and kill this. By the way, you can send these plots in the background, and then when you run another simulation, when you change parameters, you can keep them around and compare them. Now, here's the other thing that this nice tool allows you to do, is we can plot multiple files. Okay, so in this case, we're going to plot both the time domain and the frequency domain. So now we have both plots. So if you had a lot of results, you can just use this tool and plot all of them at once. You can also take that command for the Java, going to the tools and IIP plot, and put it into a nice script, so you don't have to, type it all. We'll show that later. Basically using $1, $2, $3, etc. for the various plots, and just run it. Okay, so you can do a lot of things under, of course, Unix, Linux. So one of the things I want to show is, here's the time domain. So let's go ahead and get this guy, and let's change the theme. One of the things I want to show is a lot of times in DSP, right now it shows sort of like continuous, but we might want to look at it from a discrete point of view. Okay. And in order to do that, we can go to this tool here and tell it to use bar for the style. Okay. This is very important because there you go. So now you actually know that you're dealing with discrete samples. Let's go ahead and zoom in here. And you can see that you're dealing with discrete samples. Okay, now if you want to go back to continuous, let's go over here and just say line, no bar. Okay, just line, apply, and you have the continuous. Okay, this plotting tool is very powerful. It's optimized for DSP type applications. Like one of the things we have there is like iDiagram. And we'll show a lot of its features in other simulations. One of the things we're going to show is a digital communication link, a QPSK digital communication link, where we'll show the constellation. We'll also show the spectrum, bit error rate, all of those things. Also iterative type simulations, because we have a built-in tickle interpreter in Capsim. And that's important when you're doing bit error rates, where you can change the signal noise ratio, calculate the bit error rate, and then store them in a file and then plot them. Okay, so this concludes our video. I just want to point out again, this is using Linux Mint on Ubuntu. You can use other distributions. We've also have Capsim running and verified on Arch Linux and also on Debian. Debian using ARM64 on a Mac OS using Parallels. Or if you had a native, non-Mac OS, just Debian distribution, it works well, but you have to build the libraries from the source code. That's fine. And we also have a graphical version of Capsim, which we will have another video on later, and we're going to add it to the GitHub repository as open source using Qt. Very powerful, but I want to emphasize there's a lot of merit to having a text mode version of Capsim. And as you can see from the interactions we had, it's very easy to build block diagrams out of this thing. We also have some very complicated block diagrams that we can run, including, for example, OFDM, MIMO OFDM, with acquisition to works, using text mode Capsim. And text mode Capsim is very portable, since we don't have to use these graphic libraries. It's going to be around a long time. It works, and very small footprint, very fast. The graphical is very fast. Capsim is written in C, runs very fast, and we can always link to C libraries and if needed. Okay, but for now we're just going to show how to use built-in blocks. We have different video for custom blocks. So we're going to show another useful tool called Draw Topology, again, a Java application, multi-platform. Let's go ahead and do a list, and we notice that we save the topology as sign test.t. Here it is in the directory, and we have a nice tool which will allow us to actually view the topology graphically. Now, let's go ahead and invoke that. So basically, the command is, the tool is draw topology jar, and all we need to do is give it the name of the topology, in this case, sign test.t. So let's go ahead and do that and run it. And basically, it's GPL version 3, and here we go. So it's showing the topology graphical form. So we see the sign 0 connected to print file 0, add noise 0, and then spectrum text 0. So that's the connections and the blocks. So it's a good tool for looking at the topology, even though this is a non-graphical version of Capsim, text mode kernel, but we do have this tool which comes in handy to show the topology graphically. Now, if you have a very large topology, then of course it'll scroll and you can see it all. Now, this is drawn automatically. Okay. Again, the full graphical version of Capsim, highly interactive, very powerful, written, basically linking into the Qt libraries, and is available on Linux, both Ubuntu, like Linux Mint, etc., and also Arch Linux, and been verified. Now that'll be on the GitHub website very soon, and we'll have a video on that and how to set that up. Okay. Okay, so that concludes this video.